Descriptive limits. So, descriptive limits. We are describing the behavior of the graph still. I mean, that's what limits are. We describe behavior of the graph. Descriptive limits only happen when the y values are going towards infinity or negative infinity. So, just as like a quick graph, you don't need to write this down, but let's just say I had a graph that looked like this. And maybe I was asking you, what are the y values approaching as we approach 0? The x value is 0. Well, notice that the y values are going up and up and up towards infinity, right? Or I could have had the same thing, but them going down towards negative infinity. So descriptive limits happen when we are approaching a vertical asymptote, basically. So from now on, if we're evaluating limits, like we're going to do right here, and we're evaluating them at an asymptote, vertical asymptote specifically, you want to use a descriptive limit if it exists. Now, remember, technically, the limit doesn't exist, but we can use a descriptive limit. So, let's have you guys start these two. Okay, these are the same graph, these are the same graph. If it helps you use the graphing calculator first, go ahead and do that, and then we'll talk about this. So go ahead and put me on pause. Let's focus on the function 1 over quantity of x plus 2 squared. So as we approach negative 2 from the right, we go towards infinity. As we approach negative 2 from the left, we go towards infinity. And the limit as x approaches negative 2 is infinity. Okay? Now we could think about this in multiple ways. First and foremost, okay, let's think about, let's look at my graph. I graphed this already, so I put this in my y equals. If I'm looking at my graph at negative 2, visually speaking, I can see that that limit is going towards infinity, both from the left and the right. Let's take a look at my table. Let's fix my table real quick. Doesn't matter. What are we going towards? Negative 2. Negative 2. And let's go up by auto. Okay, so now, same thing here. I probably should have done a smaller change. Sorry, guys. Bear with me. Let's go 0.1. Okay, so you can kind of tell a little bit coming from the left-hand side, coming from the right-hand side, that these values are getting very big. And if I made that difference like 0.01 or whatever, it would be even more obvious. Okay, so table of values, I can also see that. Again, these are descriptive limits. Let's look at this one. And notice that the limit as x approaches negative 2 from the right is infinity, but when we approach negative 2 from the left, it's negative infinity, which therefore means that the limit does not exist. Again, graphically speaking, I have this in my calculator. We're approaching negative 2 from the left, approaching negative 2 from the right. Doesn't approach the same value, so it doesn't exist. I could also look at my table. Right? So you guys can kind of see that same behavior going on as we talked about in the last one. Okay? Again, these are descriptive limits. So what is occurring at negative 2 in both of these functions? Vertical asymptotes. So let's talk about vertical asymptotes. Remember, vertical asymptotes exist in rationals. We also studied and saw vertical asymptotes in logs. It says here, if f of x approaches infinity or negative infinity as x approaches c from the right or the left, then the line x equals c is a vertical asymptote of the graph of f. Another way we can think about it is let f and g be continuous on an open interval containing c. If f of c is not 0 and g of c is not 0, then there exists an open interval containing c such that g of x is not equal to 0 for all x doesn't equal c in the interval, then the graph of the function given by h of x equals f of x over g of x. This is just kind of relating it to the idea of being a rational function. So let's play around with some examples. It says find the vertical asymptotes for, if any, of the function f of x. So let's see what you guys remember. Hint, you'll need to start factoring. So find the vertical asymptotes. Go ahead, put me on pause. So, like I said, factoring. In the denominator, I took out a GCF first, then I did grouping, factoring by grouping. This x plus 3, x minus 3 comes from x squared minus 9. And then, in terms of determining my vertical asymptotes, well, we get 1 at 3, and we get 1 at 0. What about negative 3? And what about 2? Well, there's actually some holes that will exist at those values. I only have 2 vertical asymptotes there. Just some good review. Okay, now we're going to evaluate. And, we're looking for descriptive limits here. So, what I'd like you to do is I want you to try this on your own first, and then we'll talk about this together. So go ahead, put me on pause. Well, maybe you needed to graph this, and if you did, that's totally fine. I mean, we're still in our beginning stages. First thing I did is I said, okay, well, there is a vertical asymptote at 1, and we're being asked to evaluate the limit as x approaches 1 from the right. So what would it look like if I plugged in some kind of number that's to the right of 1, on the positive value of 1? What would happen? Well, I get 2 plus, I just chose 1.01. I plug that in, and I notice that I get a positive over a negative, which means that this limit is going to approach negative infinity. Okay? Again, you can graph it if you want to verify. For this one here, the same thing. I said, okay, there's a vertical asymptote at 0, for sure. So what would it look like if I plugged in values that are slightly to the left or negative of 0? So I took the limit of the difference, because we know that that's a rule for limits, property of limits we can use. No matter what I put in here, it's going to go towards 0. Again, this is a limit. Minus, let's say I plug in negative 0.01. Well, I'm going to get minus a positive or over a negative. So it's minus a negative, so this will be positive infinity. Got some properties of infinite limits, or in other words, descriptive limits. So let C and L be real numbers, and let f and g be functions such that the limit of f of x as x approaches c of f of x is positive infinity, and limit as x approaches c of g of x is some real number L. So our sum and difference property says that if I add or subtract their limits, remember, I'm having infinity, and I'm adding or subtracting L. It's still going to equal infinity. Product. If I'm going to multiply them, so if I multiply their limits together, and assuming that L is a positive value, this will still be positive infinity. So positive real number times infinity will be positive in terms of limits. If I'm multiplying them, and let's assume that L is negative in this case, then it will approach negative infinity. And last property, the quotient property. If I divide, remember g of x, that limit is L, doesn't matter if it's positive or negative, and let's say f of x is infinity. Well, if we keep dividing by really, really, really large values, it will equal 0. This will be helpful for us in evaluating. So let's go ahead and try this one. Go ahead, put me on pause. You can try both, actually. Hopefully you didn't fall under my trap here. Remember, always look to do direct substitution first. You might not always have to use these other sneaky methods. So I did use direct substitution. Even though we're approaching 1 from the left, I can still plug in 1, and this limit equals 0. Now this one, if you do look to do direct substitution first, you notice that you can't do it, right? Plug in 3, divide by 0. What? 0 would have a fit. So I noticed that there's a vertical asymptote at x equals 3, and since we're approaching 3 from the right, I plugged in a value that is slightly above 3, just so we could understand the behavior of the graph. And when I do that, I notice I'm going to get a positive over a positive. So this approaches positive infinity. Okay, let's take a look at this one. Says the cost in dollars of removing P% of the air pollutants from the stack emission of a utility company that burns coal to generate electricity is this. So, part A, I want you to find the cost of removing 90%. Then, I would like you to find the limit of C as P approaches 100 from the left and interpret its meaning. We love when students interpret meaning. Okay, go ahead, put me on pause. Okay, so finding the cost of removing 90%. So I plug in 90, because P represents the percent of air pollutants. Plug in 90, I get 720,000. So don't forget, the word problem, the cost of removing 90% of pollutants is $720,000. Now I wanted to find the limit of C as P approaches 100 from the left and interpret its meaning. So let's start with the nitty-gritty math part. If I find the limit as X approaches 100 from the left, well, first of all, we know that 100 is a vertical asymptote, right? So I'm just going to plug in a number that's a little to the left of 100. So like 99.9, whatever it takes, okay? And I would figure out that it's a positive or a positive. So I know that it's going to be infinity. Well, we wanted you to interpret its meaning. Well, think about this. We have 0% of pollutants to 100% of pollutants. So what this means is that the cost of trying to remove all pollutants, or in other words, 100% of pollutants, will become infinitely large. All right. Another example. It says find two functions f and g such that the limit as x approaches c of f of x is infinity, and the limit of g of x as x approaches c is infinity. But when we subtract, so the limit as x approaches c of f of x minus g of x, that it's not 0. FYI, there are many correct answers here, so if you're not even sure where to start playing around with functions. But you got to get this condition first. So go ahead, put me on pause. Said there are many correct answers here. So here's just one example of a correct answer that I chose. So I said let f of x be 1 over x squared and let g of x be 1 over x to the fourth. Both of these have a limit as x approaches 0 that goes towards infinity. There's a vertical asymptote at 0. But when you subtract them, their limit as x approaches 0 actually is negative infinity, not 0. Which a lot of times people think 0 because they're like, oh, infinity minus infinity, but that's not the case here. Because think about what would happen. And you can also show this on the calculator, on a table, graph, whatever that is. But like I said, there are many correct answers. And if you came up with a cool example of your own, please show me. It's really cool for me to see these things, and it's cool when you guys come up with your own. So, all right, part 2.